All right, so in this video, we're going to talk about the surface integral of vector field now, vector field F over surface S. And we'll define this as our flux. And so traditionally, it's going to be your F dot N ds. And that's very, very common notation. That's essentially what it is. But we're going to use the form F dot gradient of G dA. So what we're saying, and we'll use this again later as well, we're saying this N ds is going to equal the gradient of G dA. Now, one thing to remember, one thing that you'll probably want to look at in your text is this surface S. The surface S needs to be a two-sided orientable surface. And orientable is kind of a weird thing to think about. If you're familiar with what's called a Mobius strip, you could see that would be not an orientable surface because as you walk along the Mobius strip, you might be on the top, you might be on the bottom, and you might not have ever switched, which is as crazy as that sounds. So I would encourage you to look at page, let me write it on here real quick. So look at page 1012 to get a better visual of that two-sided orientable surface. All right, so to get this thing going, I'm going to go ahead and let S be a surface such that capital G of XYZ equals 0. So then if Z equals G of XY, then our capital G of XYZ is going to be Z minus G of XY equals 0. Now, the reason why it's so important to get this set up is, again, we're going to be using this gradient G dA. So when I use this guy right here to come up with my gradient, you'll see what's going to happen. So my gradient of G, if I take the gradient of this guy right here, partial with respect to x would be a negative G sub x. So negative G sub x. That's going to be the negative from this guy, partial of G with respect to x. Similarly, with respect to y, negative G sub y. And then with respect to z, we're going to get a 1. So the partial of this guy with respect to z is just going to give us a 1 right there. Now, this is going to be used provided we are oriented up. And that comes into play when we talked about our orientable surface from earlier. Now, if we're oriented down, it's really not that much more complicated because we'll just go ahead and put a negative out in front of that gradient of G. And now we're going to have G sub x positive, G sub y positive, and a negative 1. So this one's going to be used when we're oriented down. And once we get into our example here on the next screen, you'll see how this comes into play. But I found that following this setup over here, given these conditions right here and these gradient vectors, is much easier to manage than pushing through with some of the unnecessary notation that you might find other places. All right, so in this example, we're going to compute the outward flux. We've got our vector field F, and we're over our surface S bounded by the solid of the cone and then the plane. And so it is somewhat important to see how this looks. So maybe I'll just sketch that in up here where we've got our cone coming up like this. And then we're going to be bounded by that plane, Z equals 3, so something like that. So this is the surface here that we're talking about. We've got the cone and then we've got the plane up here. And so what's going to be interesting is two things. First of all, we're bounded. So essentially we're going to have two different surface integrals to compute. And we'll say that when we compute the total, we'll go ahead and add S1 plus S2. And I guess to be clear, those would be double integrals. Not that it really matters a whole lot at this point. But we're going to have two things. We're going to have the top surface, and then we're going to have this bottom, if you will, surface. And another thing to point out with this is that you can see the arrows or the direction of things passing through. One would be clearly up, and one would be clearly down. So when we're talking about the orientable surfaces, anywhere along this plane, we would be oriented up. anywhere along this cone right here, we would be oriented down. And so those are going to be two very important things to keep track of. So I'm going to go ahead and get started here by starting with S1. Now, S1 I'm just going to treat as z equals 3. And so my g of xyz would be z minus 3. Okay? Which tells me my gradient of g is going to be 0, 0, 1. So if I take the gradient of this guy with respect to x, I get 0, y I get 0, and z I get 1. And now that's pretty interesting because of a couple things. One thing to keep in mind is that we are oriented up. So this truly is going to be that vector we're talking about. Earlier, I mentioned this gradient of g was somewhat replaced from that n vector. And that n vector was that normal vector, right? Well, if you look at this plane, a normal vector to the plane would, of course, be your k vector, 0, 0, 1. So if anything, I hope this gives you confidence that my n.ds, or excuse me, my nds is equal to my gradient g dA. All right, so now I'll go ahead and take my f and dot it with the gradient. And this one we could probably do in our head. When we take this guy right here and dot it with this, we'll get a 0 from that guy, a 0 from that guy, and then we'll just have that 3z squared left there. So gradient g dot f ends up being 3z squared. So that double integral now with s would be 3z squared dA. And so now, since we're talking dA, of course, that means we're back down in R2, and that's going to be xy. And if z equals 3, and I plug a z right there, that's going to give me my x squared plus y squared equals 9. So x squared plus y squared equals 9, which is a circle centered at 0, 0 with a radius of 3. So when I get this part set up, I would probably go with the fact that since z equals 3, I can plug that in. That's going to give me a 27. Additionally, the dA would probably make more sense to go polar since we're dealing with this circle. So my dA is going to be r dr d theta. We'll go from 0 to 3 and 0 to 2 pi. So there's your setup now for this first part, S sub 1. And so then we'll have our S sub 2, which will be this bottom part here, and we'll add the two things together to give us our total outward flux. So let me go ahead and move this up a little bit here. And so for S sub 2, this is where we're going to be studying the z equals the square root of x squared plus y squared, which means our g of xyz would be z minus the square root of x squared plus y squared, and then our gradient of g. So let's just go ahead and compute the gradient of g as is real quick. So with respect to x, we would get a negative x over the square root of x squared plus y squared. For y, we'd get a negative y, very similar, over the square root of x squared plus y squared, and then we get that 1 for the z. Now, it's important to remember the conversation we had a little while ago about how this arrow right here will show this surface would be oriented down. And so we don't want to use this gradient vector, but instead I'm going to come through and I'm going to put a negative out in front, which would turn this positive here and here, but would make this guy negative. So that's the vector that we're going to use then to dot with f. So I'll say negative gradient g dotted with f. And this one gets a little bit messier, not in a way that's not going to work out nicely, but it is going to be a little bit messier. So we're going to take this guy right here times this guy right here plus this guy times this guy plus this guy times this guy. So it's just a traditional dot product, but it is, again, a little bit messier. So when I do this, that's going to end up giving me an x cubed plus 2y cubed minus 3z squared square root x squared plus y squared all over the square root of x squared plus y squared. And so that is truly what I'm going to end up dropping in front of this integral right here. Now, to be fair, when I do this, I would probably, if I was going to go ahead and evaluate this, I would probably use polar coordinates because you can see the x squareds and the y squareds are a big part of this. But regardless, I'm just going to go ahead and drop it in there real quick to give you guys the official setup. And so then we would have our dA as well. And so from this stage, really the meat of it's done. Again, I would probably go into polar coordinates if I were going to evaluate this, much like I did up here. But at the same time, you can do whatever you want to do. You can see that we do truly have our x's and y's only in here, so there aren't any z's you have to worry about. So this guy right here would be a very informal setup for that last part. So to kind of summarize, this guy right here would end up giving us a 243 pi. This guy right here would give us a negative 243 pi over 2. And so, as I pointed out up here, the overall outward flux would be a 243 pi minus 243 pi over 2 to give us the final answer of 243 pi over 2. So we did something similar back when we studied line integrals as well. Now for surface integrals, it's really no different.